All right, so this is section 5.1. Completely messed up the chapter there. So we're going to be talking about area between curves. Now, technically, we've already been doing it. When we've been finding area between whatever the curve has been and the x-axis, technically that is area between curves. The x-axis technically is y equals 0, so it is a curve. Now we're going to be able to do it between two other curves, not necessarily the x-axis. All right, so in order to do this, we're going to start off by determining the area between a curve and the x-axis like we've been doing before. So if we want to look at the area under y equals x squared from 0 to 2, do my best here to sketch this pretty well. Let's see, we're going to have 1, 2, 3, 4, 1, 2, 3, 4. Trying to draw this as good as I can here. So from 0 to 2, y equals x squared is going to look like at 0, it's 0, at 1, it's 1, and at 2, it is 4. So it's going to look something like that. So there's your parabolic shape. The area from 0 to 2 is going to be this region in here. And we know how to find that. We just take an integral, which is going to be the integral from 0 to 2 of x squared dx, which will be 1/3 x cubed evaluated from 0 to 2 using fundamental theorem. So plugging in a 2, we are going to get 8/3. Plugging in a 0, we get 0, so our area is 8/3. Now let's say we wanted to find the area under the curve of y equals x plus 2 from 0 to 2. So once again, let's sketch that. 1, 2, 3, 4. 1, 2, 3, 4. So let's see, x plus 2 is a line with a slope of 1. So y-intercept of 2. If I do a rise over run of 1, up 1 over 1, up 1 over 1, we're going to end up with that linear piece right there. So then if I wanted to find the area under that curve, I would be talking about this area right here, which is really nothing more than the area of a trapezoid. So I could do it by using geometric shapes, or we could actually go ahead and do the integral. I'll show the integral here of x plus 2 dx. So antiderivatives are going to be 1/2 x squared plus 2x from 0 to 2. Plugging in a 2, 2 squared is 4, half of that is 2, plus 4, and then plugging in a 0 gives you nothing, so we get 6. So what if I wanted to find the area in between those two curves? Well, I kind of drew the graph the way I drew it on purpose, so you can kind of see that the area of that trapezoidal region is really going to be a greater area than the other one. So if I wanted to find the area between the two curves, the concept is, let me see if I can draw this one more time. 1, 2, 3, 4. 1, 2, 3, 4. The concept is if I take the area of the bigger region and I subtract the area, I'm going to do this in a different color here, of the smaller region, so the area of the bigger region is all of this, and if I subtract the area of the region underneath of the x squared curve, what that should leave us with is all of this space. This was horrible. Probably should not have tried to erase that. Whoops, wrong color. Yeah, I'm just messing this all up, aren't I? There. What that should leave us with is that white space, minus that one little thing at the top there. There, something like that. So if I take the area of the entire trapezoid, subtract the area under the parabola, then I'm going to get that white space. That's the area I'm looking for, the orange. So, as you might expect, I can take the integral of the trapezoid minus the parabola. And that will give me the actual area. Now, I'm not going to go ahead and integrate this one. We're going to do plenty of that throughout the rest of the video. But in this case, we already know that the area of the trapezoid region was 6. We know that the area of the parabola region was 8/3. So if you do 6 minus 8/3, you end up with 10/3. So the area of that orange region is 10/3. So the idea is, if you take the area of the larger region, you subtract the area of the smaller region, which is integrating both areas, doing a subtraction, you're going to get the area in between the two curves. And that's the concept. That's what we're looking for. Okay, so let's go ahead and put that into words. So if I wanted to find the area, the integral from a to b of f of x minus g of x, as long as the f of x is the greater region and g of x is the smaller region, I can do the integral of the greater minus the smaller, and I will get the area in between. All right, so let's look at example 2. Find the area of the region bounded by y equals x squared and y equals square root of x. So that's a key word there. It says that it is bounded by those, because what you should notice is they did not give us the bounds, which means that we need to figure that part out. So first thing, graph the set of equations. All right, so what I know is that y equals x squared is your parabola. I also know that y equals the square root of x only occurs basically in the first quadrant there. So y equals square root of x looks kind of like this. Starts to level off a little bit. And then y equals x squared does that. So the area in between them is going to be this area in here. So the question is, where do they intersect? This is where we have to do a little bit of work. Finding the points of intersection, well, you should remember to find the points of intersection of two things, you set those two things equal to each other, and then you can find where they intersect. Because really that's what we want to know, is where they are equal, where they are the same. So we're going to set x squared equal to the square root of x, and we're going to solve that algebraically. We want to get that square root of x out of the square root, so in order to do that, we will square both sides. Squaring x squared will give you x to the 4th. Squaring the square root of x will give you x. You don't want to divide an x out of this, because you will lose one of your solutions. So don't divide this and say, oh, well, x cubed equals 1. That is a true statement in this case, but it's going to lose a solution. So what you want to do instead is subtract x on both sides, get one side to equal 0, and then we'll factor. So we can factor a common factor of an x out, and then we can set each one equal to 0. So had you divided, you would have lost the x equals 0 part. And then we'll set the x cubed minus 1 equal to 0, which means you'll add 1 to both sides, so x, taking the cube root, is 1. So our intersections are 0 and 1. And that might have been intuitive. You might have been able to see that anyway. This is not one of the more challenging ones to do, but just in case they get a little more challenging, this is kind of the concept. That's what you have to do. All right, so the last thing is we actually take the integral. So I'm going to integrate from 0 to 1. Those are the two intersections that we just found. Looking at our graph here, it looks like that square root function is the greater function. So it's the square root of x, and then minus, pen's just not working well for me here tonight. There we go. Minus the smaller function, which is x squared dx. Okay, and then we'll go ahead and take antiderivatives. So the antiderivative of square root of x, x to the 1/2 becomes x to the 3/2 and then multiply by the reciprocal 2/3 minus antiderivative of x squared is 1/3 x cubed, evaluated from 0 to 1. Plugging a 1 in, I'm going to get 2/3 minus 1/3. Plugging a 0 in, we get 0. So 2/3 minus 1/3 is 1/3. That is the area between those two curves highlighted in red. Okay, let's move on. Here we want to find the area bounded by the curves 2y squared equals x plus 4 and y squared equals x. These curves are getting a little bit more challenging. One thing you have to recognize is that these are parabolas. However, the y is the squared part this time, not the x. So that means these parabolas open sideways. So when we sketch this graph to kind of get a good idea what it looks like, again, you kind of have to know what these graphs look like. If this first one here was y equals x squared, you'd know it looks like your standard parabola. Instead, it's x equals y squared. So that's going to be a parabola which opens to the right. Okay, that's x equals y squared. And the easiest way to think about that is if it was y equals x squared, it would open up because everything would be in the positive y area. But since it's x equals y squared, no matter what value I plug in for y, I'm going to square it, and then I'm going to get out a positive x. So all of the x's have to be positive, therefore it opens to the right. So this is x equals y squared. Now, in order to solve this problem, I basically need to put the other formula into x equals something as well. So it's all in terms of y. So really, I'm going to take that first one and I'm going to subtract 4 on both sides. So what I get is 2y squared minus 4 equals x. All right, so the minus 4 part in normal shifting would mean you would move something down 4 units. In this case, because we're doing it in terms of x, we're going to move it left 4 units because, again, left is the negative direction, right is the positive direction. So our parabola is going to start 4 units to the left. That's where the vertex is going to be over there. Now, the 2 out in front of the y squared actually, if you remember anything about your shifting and your stuff as far as how numbers affect the shape of these things, is going to shrink. I don't want to say shrink. That's not the word I'm looking for. Make the parabola skinnier. Probably the easiest way to say it. So it's going to look something like this. It's going to be a skinnier parabola. It will still be a parabola. It will just be skinnier. So this is your x equals 2y squared minus 4. So what we're looking for is the region which is bounded by these two. That means it's got to be in between these two. So we are looking for this region in here. So that red region in there. So now one of the things you might look for is, okay, if I was to take this and go from, I don't know the best way to say it, my bounds here are not going to be in terms of x. They're going to be in terms of y. All right, and there's a couple of reasons for that. First of all, when we do the area in between these curves, remember that the idea was you're creating rectangles when you're finding the area. So if I created a rectangle the way I normally would, and the rectangle would be vertical, over here, there really wouldn't be much of a problem. I could create a vertical rectangle in there. Granted, that's a really big rectangle, but remember, these are supposed to be infinitely thin rectangles to add up the areas. But I would be going from the same top function to the same bottom function. Okay, that's going to be a challenge. Plus, when I get over to here, I'm going from this function down to here, and then I'd have to split it to go from that function to there. So really what we're doing, instead of doing rectangles in that fashion, we're actually doing rectangles right to left. So my rectangles now look like this. And then I can put rectangles everywhere in here. I'm obviously not connecting them, but you get the idea. And there would never be an overlap. There would never be a reason to break it. So basically, my rectangles are going to be formed with a change of y, so a dy, which means that in this case, my bounds also have to be in terms of y, which is really nice because of the fact that we've actually already solved each one of these two things for x. I can set the two equations to each other and solve for the y bounds, which is actually what we're going to do. So we're going to have 2y squared minus 4 equals y squared. Now we can find our y bounds. So I'm going to subtract one of the y squareds to the left, and we'll get that y squared minus 4 equals 0. So you can either choose to factor this to y minus 2y plus 2, or you can add the 4 to the right side. Just to remember, when you take the square root, you'll have the plus or the minus 2. One way or the other, you get that y is going to be positive or negative 2. So now we have our bounds. Now we can go ahead and integrate. So I'm going to integrate from negative 2 to 2. Now, which is the greater function? Well, remember that right is a positive and left is a negative. So the green in this case is the rightmost or the uppermost part of that rectangle, and the blue is the lowermost or the least part of those rectangles. So the green function, y squared, is the greater. And then the 2y squared minus 4 is the smaller function. And it's now dy, because we are now doing this as the y's are the change of the rectangle's bases. So everything with respect to y. All right, so I strongly suggest when you do these, simplifying algebraically within your integrand first, then taking your integral. So y squared minus 2y squared is negative y squared. Distributing the negative in there, you're going to get plus 4 dy. Now we'll take our antiderivatives, so we get negative 1/3 y cubed plus 4y, and we will evaluate that from negative 2 to positive 2. So plugging in the 2, you're going to get negative 8/3 plus 8 minus. Plugging in the negative 2, negative 2 cubed is negative 8, so that's going to make that a positive 8/3, and then minus 8. And you might look at that and say, oh, it's going to be 0. It's not going to be 0. Be careful, you're subtracting. So really what you've got is a negative 8/3 minus 8/3. Well, that's minus 16/3. Then you've got an 8 minus a minus 8. So that's really plus 8, so that's plus 16. And then 16 in terms of thirds is going to be 48/3. So negative 16 plus 48 is 32/3. And there's the area between those two curves. All right, so now you might have also come up with another question. Well, how exactly, if I don't sketch these things, would I know which is the greater and which is the lesser function? That's a really good question that I am going to answer for you in a couple of these next problems. So let's go ahead and take a look at example 4. Actually, let's come back with another video and we'll do that in the second video.